Light shapes everything you see. It fills the sky, it carries color, it moves faster than anything else we know. For over 100 years, scientists have argued about one simple question: is light a wave, or is it a particle? Most textbooks give a safe answer. They say it is both, but that answer hides a deeper truth. Light is neither. This is not a theory meant to confuse. It is a conclusion forced by experiments that refuse to agree with each other. Experiments that broke old rules. Experiments that made some of the greatest physicists doubt their own ideas. In school, we are taught to divide the world into clean categories. Waves move smoothly through space. They spread out. They interfere. Water waves do this. Sound waves do this. Particles are different. They are small objects. They hit things. They arrive at specific points. A ball thrown through the air is a particle. At first, light seemed easy to place. Early experiments showed light bending, spreading, and forming patterns. That behavior matched waves, so scientists called light a wave. Then something strange happened. Other experiments showed light arriving in sharp, sudden bursts. Energy came in fixed amounts, not smooth, not continuous. Light knocked electrons out of metal as if tiny bullets were hitting them. That behavior did not belong to waves, so light was called a particle. The photon was born, but the problem did not end. When scientists tried to treat light only as a particle, predictions failed. When they treated it only as a wave, predictions also failed. No single picture worked. The universe refused to choose. This led to one of the most uncomfortable ideas in science. Light behaves differently depending on how it is measured. Not because light changes its mind, but because the old categories are too small. Wave and particle are human labels. They come from everyday experience. Light does not care about everyday experience. Some experiments show interference patterns, even when light travels one unit at a time. Other experiments show single points appearing, even when no solid object is moving. Both results are real, both are repeatable, and neither fits the old definitions. This forced physics into a new direction. Instead of asking what light is, scientists began asking how light behaves, not as an object, not as a ripple, but as something described by probabilities. Light does not travel as a tiny ball. It does not spread like water. It follows mathematical rules that describe chances, not paths. The strange part is this: the math works perfectly. The pictures do not. Light is governed by equations that predict outcomes with incredible accuracy. Lasers rely on them. Satellites rely on them. Modern technology would collapse without them. Yet no simple image explains what light truly is between emission and detection. That gap is not a failure of science. It is a limit of human intuition. The wave model is useful. The particle model is useful. But neither is reality itself. They are tools, approximations, shortcuts for understanding behavior, not essence. Light exists as a quantum entity. It follows rules that do not belong to the classical world. Rules where certainty is replaced by probability. Rules where outcomes matter more than trajectories. This is why debates about light never truly ended. They evolved. The real lesson is not about light alone. It is about nature itself. At the deepest level, reality does not follow human categories. It follows its own logic. By the end of this video, you will understand why calling light a wave or a particle misses the point. You will see why this confusion was necessary for modern physics to exist. And you will understand why some of the most important discoveries came from accepting that reality is stranger than our language. This channel explores ideas that sit beneath everyday understanding. Ideas that challenge how we see the universe. Ideas that change how we think about reality itself. Welcome to the channel. If you want to see the universe more clearly, subscribe now. When scientists first tried to understand light, they trusted experiments more than ideas. One of the most important experiments ever done with light was simple in design but shocking in result. Light was sent toward a barrier with two narrow openings. Behind the barrier was a screen. If light were made of particles, it should pass through the openings and form two bright lines on the screen. That did not happen. Instead, a pattern appeared. Bright and dark bands spread across the screen. This pattern only made sense if light was behaving like a wave. Waves overlap. Waves interfere. Where two wave peaks meet, the light becomes brighter. Where a peak meets a dip, the light cancels out. The double-slit experiment showed exactly this behavior. Light acted as if it was spreading through space and interfering with itself. For many scientists, this seemed like the final answer. Light was a wave. But this confidence did not last. Another experiment challenged this picture from a completely different direction. When light shines on certain metals, electrons are ejected from the surface. This effect depends on the color of the light, not its brightness. Weak light of the right color can eject electrons. Strong light of the wrong color cannot. This result made no sense if light was only a wave. Waves carry energy smoothly. More intensity should always mean more energy, but the metal did not respond that way. The electrons behaved as if light arrived in small, fixed packets. Each packet carried a specific amount of energy. If the packet had enough energy, an electron was released. If it did not, nothing happened. No delay, no buildup, just an instant response. This behavior matched particles, not waves. Light was acting like a stream of tiny energy units. These units were later called photons. Now physics faced a serious problem. Two experiments, both correct, both repeatable, both essential. One showed light behaving like a wave. The other showed light behaving like a particle. There was no way to ignore either result. So scientists tried a compromise. They said light must be both a wave and a particle at the same time. This idea became known as wave-particle duality. It sounded reasonable. It allowed equations to work. It allowed experiments to be explained. But it also created confusion. How could something be two opposite things at once? A wave spreads out. A particle is localized. A wave interferes with itself. A particle arrives at one point. These are not small differences. They are deep contradictions. As experiments became more precise, the cracks in this idea grew wider. In some setups, light produced interference patterns, even when photons were sent one at a time. There was no second photon present to interfere with. Yet the patterns slowly formed. In other setups, light produced single detection points, even when its wave behavior should have dominated. The result depended on how the experiment was arranged. The old words wave and particle began to feel like labels pasted onto something far more complex. Trying to force light into classical categories started to fail. Classical waves assume continuous energy. Classical particles assume definite paths. Light followed neither rule fully. When scientists tried to imagine a photon as a tiny ball, calculations broke down. When they tried to imagine it as a spread-out wave, measurements contradicted the picture. The problem was not with light. The problem was with the models. This realization marked a turning point. Instead of asking which picture was correct, physicists began asking a different question. They asked which description correctly predicts outcomes. This shift led to quantum physics. In this framework, light is not described as an object moving through space in a familiar way. It is described by a mathematical function. This function does not give a position or a shape. It gives probabilities. It tells where light might be detected and how likely each outcome is. In quantum theory, light exists as an excitation of a field that fills all of space. This field is not a wave like water. It is not made of particles like dust. It is something more abstract. When light interacts with matter, the interaction happens in discrete amounts. That is why photons appear. When light propagates, its behavior follows wave-like equations. That is why it interferes. These are not two forms of light switching back and forth. They are two limits of a deeper description. Wave functions are central to this view. They do not represent physical waves in space. They represent information. They encode probabilities. They evolve according to precise rules. When a measurement occurs, the wave function does not turn into a particle. It simply updates the probabilities based on the interaction. The detection looks particle-like. because energy transfer happens in discrete steps. The spread looks wave-like because probabilities extend across space. Quantum fields go even deeper. In this picture, particles are not fundamental objects, they are events. A photon is not a thing traveling from source to screen. It is a process. It is an interaction between fields. The field exists everywhere. The photon appears when energy is exchanged. Between emission and detection, the field evolves according to quantum laws, not classical motion. This is why no classical image truly matches what experiments show. Light is not hiding its true nature. It simply does not have one that fits everyday intuition. Wave and particle are shadows of a richer structure, useful in limited cases, misleading when taken too seriously. Modern physics accepts this without discomfort. Predictions matter more than pictures, and the predictions work with astonishing accuracy. As experiments push deeper into the quantum world, this understanding continues to hold. Light behaves exactly as quantum theory says it should, not as a wave, not as a particle, but as something that only mathematics can fully describe. As physics moved forward, it became clear that the problem was not light itself, but the way humans tried to picture it. The human mind is trained to understand the world through objects and motions we can see. We understand stones, water, wind, and sound. We build ideas by comparing new things to familiar ones. This method works well in daily life, but it breaks down at the quantum level. Light does not behave like any object we can point to. It does not move through space the way a ball moves. It does not ripple through a medium the way water does. When scientists try to force these images onto light, confusion follows. The words wave and particle were never meant to describe reality itself. They were tools, shortcuts. Early scientists used them because they had nothing better. A wave was something that spread and interfered. A particle was something that arrived at a point. Light showed both behaviors, but never fully matched either one. Over time, these words became labels that created false comfort. They gave the illusion of understanding without capturing the true process underneath. At the quantum level, light does not occupy a single form. Its behavior depends on interaction, not identity. Between emission and detection, there is no tiny object flying through space and no physical ripple spreading outward. There is a quantum description that evolves according to strict mathematical rules. These rules do not describe shapes or paths. They describe probabilities. They describe how likely different outcomes are when light interacts with matter. This subtlety is hard to accept because it removes the idea of a hidden picture waiting to be revealed. There is no secret classical image that explains everything. The equations are not hiding a wave or a particle behind them. The equations are the most complete description available. Reality at this level is not visual, it is relational. It is defined by interactions, not by objects moving in space. This shift in understanding changed more than physics textbooks. It reshaped how scientists think about reality itself. Before quantum theory, the universe was assumed to be predictable in a strict sense. If you knew the position and motion of something, you could predict its future exactly. Light shattered that assumption. Its behavior showed that certainty has limits. Probabilities are not a sign of ignorance. They are built into the structure of nature. This new view of light became one of the foundations of modern technology. Lasers depend on precise control of light's quantum behavior. They work because photons interact with matter in quantized ways. The sharpness and coherence of laser light come directly from quantum rules, not classical waves. Without this understanding, lasers would not exist. Electronics also rely on this deeper picture. Semiconductors operate through energy levels that electrons can occupy or leave only in fixed steps. Light interacts with these systems by transferring energy in precise amounts. Solar cells convert light into electricity using the same quantum principles revealed by early experiments. The efficiency of these devices depends on treating light as a quantum process, not as a classical wave or particle. Even communication systems are shaped by this understanding. Fiber optics guide light through materials designed using quantum knowledge of how light interacts with atoms. Sensors, medical imaging, and precision clocks all depend on effects that only make sense when light is treated as a quantum entity. The impact goes beyond technology. Light forced science to accept that reality is not built from simple pieces behaving in simple ways. It showed that intuition evolved for survival is not enough to describe the universe at its deepest level. The universe does not owe us familiar pictures, it follows its own logic. As experiments continue to test light in extreme conditions, the same pattern repeats. Predictions based on quantum theory succeed. Attempts to explain those results using everyday images fail. This is not a temporary gap in knowledge. It is a permanent feature of how nature works. Light stands as one of the clearest reminders that reality is more subtle, more abstract, and more surprising than the words we use to describe it. Light does not fit into the simple boxes we try to place it in. It is not a wave moving through space like water. It is not a tiny particle flying from one point to another. Every serious experiment tells the same story. Those old ideas are useful, but they are incomplete. Light follows rules that sit deeper than both, rules that belong to the quantum world, where probabilities replace certainty and interactions matter more than shapes. This is why light continues to surprise scientists. Even after centuries of study, the more carefully it is examined, the more it reveals how limited our everyday thinking can be. Light shows that reality is not built from familiar objects behaving in familiar ways. It is built from principles that challenge intuition and force us to rethink what it means to understand something. That tension between what we expect and what nature actually does is what makes physics so fascinating. If this video helped you see light in a new way, support the channel by liking the video and subscribing for more deep explorations into the hidden rules of the universe.